I have created a GitHub repository which has a user guide on AMD AI Workbench. So what I did was, in my free time I explored the AMD AI Workbench and I took some screenshots of whatever I did, and I have written some explanations around it. So I'll be going through that so that you basically know what all are the capabilities of AMD AI Workbench and what you can do with it. So as you can see, this user guide is hosted on my GitHub account. So before we get to know about what GPUs were used below the AMD AI Workbench, so let me first tell you what AMD AI Workbench basically is. So let's say you have 4 enterprise grade AMD GPUs. So AMD Workbench, AI Workbench sits on top of that, and you can use those 4 GPUs to either run LLMs off the shelf like Qwen, Llama, or you can even fine tune that LLM and use those 4 LLMs for GPUs for fine tuning or for inferencing. And if you want nothing to do with large language models, what you can also do is use that 4 GPUs as workspaces, so that you can run Jupyter notebooks on this, you can run VS Code on this, so that any programs that you run will be able to use the cluster of 4 GPUs that you have. So basically, you have some workloads, you have some activities or tasks that you want to be completed, and then you have your 4 GPUs in a cluster, and AMD AI Workbench acts as an interface between both. So before we see what type of GPUs are we using in an AMD environment, we first need to see the NVIDIA counterpart. So the NVIDIA counterpart is H200 GPU. NVL basically means NVLink, in which multiple GPUs can talk to each other. So the GPU memory that NVIDIA has is 141 GB, 141 GB VRAM, and then it can consume up to 700 watts of power. Now these two are the only important points here. Then we can move to the next part. Yeah, you remember the VRAM metric that we just spoke about, that is 141 GB. Here we have a rough approximation of what type of LLMs can run on what GPU. So if the large language model that you are using is 7 billion parameters, it can comfortably fit in a 14 gigabyte VRAM graphics card. So BF16 is basically brain float 16, meaning each parameter will be allocated 16 bits, and FP8 is floating point 8, meaning each parameter will be allocated 8 bits. Now the thing is, moving from 16 bit to 8 bit, you do lose some accuracy on the quality of output that you get from an LLM, but the size, the memory footprint required is basically halved, as you can see, with only a little hit in accuracy. So that's why a lot of people use this quantized model. This entire process is known as quantization. So here, as you can see, if you remember, the VRAM capacity was 141 GB. So in a graphic card with 141 GB VRAM, a maximum of 70 billion parameter model can be loaded if you are using it in 16-bit quantization. Or if you quantize it to 8 bits, then you can also use 70. It will only consume 70 gigabytes of the existing VRAM. And 405 billion parameters cannot be run on any single GPU. You need a cluster of GPUs to run such models. And now we discussed about quantization. Now we can also discuss about low rank adapters. So quantization basically helps us during inferencing, but low rank adapters helps us when you're trying to fine tune a model. Let's say a model was trained for general purpose task, let's say Gemma model, yeah, Gemma 3.5 billion. But if you have a specific use case, let's say you run a law consultancy firm and you want to speed up your decision making process, so you can use that existing 3.5 billion model, Gemma model, and you can train it on law specific data set. So this process of using a model and specializing it in any other domain is also known as fine tuning. So for fine tuning, if you try to fine tune the entire model, it will consume a lot of VRAM. As you can see, even if you are trying to fine tune a 7 billion model, it will consume 120 gigabytes of VRAM. But if you use low rank adapters, so if you use low rank adapters, it can fit in just under 18 gigabytes. So let me help you visualize the difference. So 120 GB, no consumer grade GPU has 120 GB of VRAM. You will need B200, H200, A100 GPUs. But 18 GB VRAM is not quite common, but you can get consumer grade GPUs like 4090, 5090, and you can fine tune your model using such GPUs. So that's where low rank adapters are used. And now let's discuss about the two concepts that are workloads and workspaces. So remember I talked about the tasks that we want to perform on the GPUs. So all of that tasks come under the workload. So for the workloads, all of these workloads are executed on Kubernetes pods, because the thing is, no one system can have like 4 to 5 GPUs. You need to have a cluster of computers with many GPUs, and all of those will be containerized, and then they will be managed by Kubernetes. And then comes the workspace. So I also told you about, you can ditch LLMs altogether. You can use the 4 GPUs, the cluster of GPUs that you have, to run your own models or develop your own application. So let's say you are trying to just experiment, you're trying to train models for, let's say, tumor detection in using MRI scans. Then you can use the Jupyter Lab workspace environment, and then you can train your own models there. Now comes AMD ROCm. Now ROCm is something that a lot of people haven't heard about, but all of us are familiar about NVIDIA's CUDA. So NVIDIA's CUDA is a programming architecture where you can use NVIDIA's GPUs to perform parallel operations. So in the same way, ROCm is AMD's answer to CUDA, right? So now moving on to the screenshots that I took when I was exploring this platform. So first of all, any model that has been deployed, and if you want to use it, you need an API key for it, right? Even when you're using, let's say, an OpenAI model in your applications, you need an API key for it, and you create it by going to platform OpenAI. You go to this website to get your own API key. So in the same way, if you have an AMD cluster and you're deploying some models on it, let me open this image for you. So here under the API key section, you can create your own API key, and then you can set the API key name, validity period, and model deployment. So what model deployments basically mean is that, let's say you have two models deployed on your cluster, one is Qwen and one is Llama, but you want this API key only be valid for the Llama model. So that you can select here. So if due to an off chance your API key gets compromised, only the attacker can only access the Llama model and not the Qwen model. And then after we have explored the API keys menu, we can go to the chat section. The chat section is basically the model that you have deployed. You can chat with it, you can converse with it to gauge how the responses are. And then we also have a comparison menu here. So what comparison menu basically does is that it compares the responses by two different LLMs or two different versions of LLM. So let's say we have Llama model. We are comparing 40 billion to 70 billion. So both of those models we can have side by side. Let's say we are asking a question like how to solve a lead code problem. So we can compare the 40 billion model and 70 billion parameter model, and we can compare the quality of responses. So not just that, you can also compare performance within quantization levels. You can compare how well does the 16-bit quantization model perform and how well does the 8-bit quantization model perform. And on top of that, you can also compare two different models simultaneously. So the solution that AMD provided it's pretty powerful because it's very feature rich. So now moving on. So that was all about what you can do if you have deployed your own model on these GPUs. So let's say you want to fine tune the model instead, fine tune an LLM instead. So for that we have the next menus. First is the data sets. So as I said, if you want to fine tune an LLM, you need your own data set on which the LLM will learn. So here you can upload your own data set. And for uploading the dataset, you will need to provide the dataset name, the data type, description, and the file that you need to upload here. And the thing is, there is a limit to how big of the files that you can upload. You can only upload up to 100 MB. If you want more, you can use Mini IO. So Mini IO is basically a local solution for Amazon S3. Like in Amazon S3, all the data is stored in buckets, right? But we can't store our local data in Amazon S3 AWS buckets because data privacy concerns. So we need all our data locally. So for that we use MinIO. So now let's take a look at AIM catalog. So AIM stands for AMD Inference Microservices. So as I told you that you can run various LLMs on your existing GPUs. So this basically acts as a marketplace for what are the different open source models that you can use. So we have many options here. We have DeepSeek, we have MetaLlama, and then we also know how many parameters does the model have. 50 billion, as you can see, 528 billion, and the tags tell you the capabilities of the model. So here in this image, most of these models are suited for text generation. So if there are some other models, they might say vision capable. So basically they can interact with images as well. So what you need to do is you need to choose any one of these model, and then you can deploy it on your cluster, and then you can create an API endpoint, you can chat with it, you can compare the chats as we discussed previously. Now this is the same thing. We have many models. As you can see, we open this image. We have Mistral model in 14 billion version, in 675 billion version. We have 24 billion version. Many different um, instances of the same model, but differing in the number of parameters. Now, what you want to deploy is totally dependent on how many GPUs that you have access to and how many you can allot for this task at the moment. Now we also have mixture of expert architecture models and tool calling models. So let me elaborate on this. So mixture of expert model basically means that, let's say we have 100 billion parameter models which is good at math, coding, writing and creative task. And let's say each of these tasks has been allotted 25 billion parameters each. Now I'm simplifying here. So we have this 100 billion parameter model loaded, and let's say I am asking the model a coding problem. So now we know that the only 25 billion parameters are allocated for coding. So instead of using the entire 100 billion parameters for inference, we are only using those specific 25 billion parameters. So the thing is, the inference latency is reduced, and the tokens per second also increases, because not the entire model is being considered while inferencing. So why is it called mixture of experts? Because if we take an example of this 100 billion parameter models, we have 4 experts for math, coding, for creative thinking, and writing, right? So we have these 4 experts, and we have this mixture of 4 experts, and based on the task that we want to perform, there will be a router which will decide. Like let's say if I'm asking the LLM to solve a math problem, now the router will decide which expert should this query go to, and then we'll get the appropriate response from there. Now this approach does have its own disadvantages. First of all, there is a lot of VRAM required for this method, because let's say I just wanted to perform some coding operations, only a 25 billion model must have sufficed for this, but we are loading the entire model into the VRAM. uh, so this also increases redundancy, because the other experts we are not using. So as I told you, from this catalog you can click on these 3 dots and deploy any model of your choice, and then it will be deployed on your existing cluster. And then all the models here, you can see the deployment status, which models are deployed, not yet deployed, and which models are still getting deployed. So the pending status is for that. Now we can begin to fine tune our own model. So for that, we just looked at the catalog section and the dataset section. So this is the model section. So here, as you can see, we have a fine tune model button. So let's see how we fine tune it here. So here, when you click on the fine tune model button, you need to provide a name for your model and select a base model. So to fine tune a model, you need a model that you're fine tuning, right? A foundation model. So let's say if you are choosing Gemma 70 billion model, that is what we are going to be choosing here. Then the training data set that we want the LLM to specialize on. And then we need to also add the Hugging Face authentication token. Why is that? Because like models like Llama and Gemma, even though they are open sourced, you still need to accept their end user license agreement. So for that, you need a Hugging Face token here, right? As you can see, we are selecting a base model here. So here we have all these models to be chosen as the base model. And after that we can click on start training, and then we can go to the deployed models page. we were we were previously at the custom models page where we were defining our fine tuning job, and the deployed models page is empty because it takes a time to for all the statuses to be updated and the training jobs to show up here. And then we can go to the secret section. The next section is the secret section. Remember I talked about MinIO. So MinIO is AMD's answer, not AMD's answer, the solution that AMD uses in instead of Amazon AWS S3 to keep the data with you. So for your model to access the data set which is not stored in the memory, it needs to access this S3 bucket. So for that you will need a credential token. So here all of that is stored under secrets. Then after we are done with loading our data, we also need to rotate the credentials periodically so that the even if the credentials get compromised, the attacker won't be able to use it for long because the keys will be rotated by then. And here you can see what are the specifications of the given workload, the name, the cluster that has been allotted to, the number of GPUs. We are only using one GPU for this and only a fraction of VRAM in that one GPU, and the URL that you can use to access the cluster it has been deployed on. Then you can also go to the logs menu that is located here, and in the logs menu you can choose the log level and as well as the event. We'll delve deeper into it. So here we have many log levels: trace, debug info, unknown, warning, and error. So all of this define how much information do you want in your logs. So trace is the most verbose level and error is the least verbose level. Then you can also have logs based on your workload or your events. So events is mostly about the cluster management, when the cluster was spun up, what is the node affinity, all of the events related to the Kubernetes architecture are in the events log, and the workload log, it is all about the model deployment, the model fine tuning, checkpointing. It contains all the events about the models instead. Then we can also enable live log streaming so that we can get real-time logs here. Then we can move on to workspaces. So whatever we did till now was about running an open weight LLM on your GPUs or fine tuning the said LLM on your GPUs. Now you might also want to use the GPU cluster that you have for your own training purposes. So for that we have a few options. You can either run a Jupyter notebook on top of the cluster. You can use a Visual Studio Code IDE on top of that. You can use Comfy UI text to image, which is basically a stable diffusion portal, and MLflow for tracking your ML experiments that you're conducting. So we are going to launch each one of these. So first we are deploying Comfy UI here. So when you deploy a said workload, you need to give the name, container image, and then quick deploy. Or you can also go to the advanced menu and you can customize the resource allocation, how many resources that you want to give to your workload. So we have chosen one entire GPU, and out of the 125 GB VRAM that we are just allocating a 32 GB VRAM. And the CPU cores that we have 24 cores. We are just allocating one core out of this, and then we can click on quick deploy. So after that, your workspace is running, and then you can also click on undeploy to destroy the existing workspace. Now in the same way, we have also deployed the MLflow tracking server, Jupyter Lab tracking server, and VS Code. MLflow tracking server, Jupyter Lab, and VS Code. All of the menu options are pretty much similar because there is the same underlying cluster which is being used. And then you can also categorize or filter your workspaces based on whether it's development, MLOps, or GenAI tools, as shown here. And here we just have the summary of the user guide that we have already covered everything, like how much VRAM is allocated for various model sizes, various quantization levels. So that was it for this user guide for AMD AI Workbench. I'll be creating more such user guides for various different technologies.